So chapter 14 is about aqueous solutions and colligative properties. And remember that aqueous means a substance has been put into water. So it's now a water-based solution. So in 14.1, we'll talk about some properties that happen to certain types of compounds when they're in solution. And we'll also talk about a unique way to write a chemical formula. But just as a reminder, remember that ionic solids are crystalline structures. They're made out of crystals, very organized and repetitive patterns. And within this ionic solid, we have ions. We have charged particles that are held together by ionic bonds and ionic attractions. So the best example is sodium, Na, and chlorine, Cl. Sodium a metal, chlorine a nonmetal, group 1 and group 17. And when they ionize, sodium becomes positive and chlorine becomes negative. We know that opposites attract, so they get pulled together and held together by those ionic attractions. So what does it mean to dissociate? So dissociation basically means to separate. And specifically, we're talking about ions separating when they are dissolved in an aqueous solution in water. So dissociation is the separation of ions when an ionic compound is dissolved, most specifically within water. So for example, again, the most common ionic compound, NaCl. So when it is in an ionic bond, there are no charges because the positive and the negative have come together and neutralized. And of course, we're adding water. And that's going to yield Na plus, Aq meaning aqueous in solution, and Cl minus, once again, Aq in aqueous solution. So what happens is you take some NaCl, table salt, and you put it into water, and what happens is the water pulls apart the ions, and you're left with Na and Cl as separate charged ions. Another example, similar, is calcium chloride. So once again, the same thing would happen. You've got calcium that becomes a positive ion in water, and then chlorine once again becoming negative. And we're just looking at these charges because that would be referring to your periodic table. So sodium's in group 1, it has a +1 charge. Chlorine in group 17 has a -1 charge. Down here, calcium has a +2 charge because calcium's in group 2 with a +2 charge. And then we have a superscript, we have a coefficient in front of chlorine just to balance it out. Okay, so looking at this compound, I would like you to pause the video and try to determine what will this compound break apart into when it's in water. So water is going to be represented by Aq. So even though we're not writing the H2O on the other side, it is represented. So what do you think? So pause the video and see what you think. Okay, if you're confused, if you paused the video, it's because I have a typo. Let me fix that for you. This should not be Na4, it should be NH. I apologize for that. So NH4. I know I kind of covered the 4 up there. So NH4Cl, which is ammonium chloride. Now try it out. Oh, I think I have the video showing you the answer already. Well, in that case, free for you. So what happens is the ammonium and the chlorine break apart. And sometimes we forget that ions can be compounds as well. So NH4 on your radical sheet has a +1 charge. And then once again, chlorine, a negative charge. Okay, hopefully that's it for my typos. So try this example by yourself. NaS, sodium sulfide, added to water. So give that a try. Okay, I'm sure you broke it apart correctly into the elements. So sodium and sulfur, but did you get the charges right? And that's the biggest concern, is not only the elements breaking apart appropriately into ions, but the charges. So sodium plus 1 because it's in group 1, and we don't write a 1 in the charge section. And then sulfur is going to be at -2 charge because it's in group 16. So you do need to consult your periodic table there. Now these are not balanced. If you want to take it further, you could balance it. So another thing you need to remember is to always put the AQ, because it has to be, water has to be represented. You can't just get rid of water completely. That doesn't happen. Also notice that it's a 2 minus charge. That's how we write it, not a -2, not a -2. It's 2 and then the charge comes after it. Okay, give this one a shot. So we have barium nitrate added to water. Did you get Ba2+ and then NO3 -1? Now I said the 1's not there, but it's considered a 1. So barium is in group 2. So it has a +2 charge. And then if you look at your radical sheet, nitrate is a -1 overall. And we're not looking to cancel the charges at this point because we're breaking it apart into the actual ions. A little bit different than Chem 1 because we're doing a different concept. Once again, this is not a balanced equation. You could take it a step farther and balance it if you wanted to. Okay, so that's just a brief overview of ionic compounds and how they dissociate in solution. Now let's talk about solubility rules. So solubility rules for precipitation reactions, and precipitate, we can write PPT. And precipitate, before I go on, precipitate basically means to come out of solution. So you have a solid that falls out of solution and then you can see it. Okay, so the first rule is most sodium, potassium, and ammonium compounds, CMPD abbreviation, are soluble in water. So if you see a compound that has one of these in it, it is soluble in water, for the most part. Second rule, most acetates, nitrates, and chlorates are soluble in water. So if you see any of those, soluble, meaning they will dissolve. Most chlorides are soluble in water, except if you have silver chloride, mercury 1 chloride, or lead chloride. Another exception is lead chloride can be soluble, but it has to be in hot water. And usually we don't use hot water to make solutions. Okay, most sulfates are soluble in water, except for barium sulfate, strontium sulfate, and lead sulfate. Most carbonates, phosphates, and silicates are insoluble. However, if you have sodium and a carbonate, phosphate, or silicate, potassium, or ammonium, it will be soluble. And this kind of piggybacks on rule 1. And then lastly, most sulfides are insoluble. However, if you have calcium, strontium, sodium, potassium, or ammonium sulfide, they are soluble. Once again, some of that piggybacks on other rules. So now we're going to look at some specific examples. So I don't expect you to memorize these. You can consult them when you're answering questions. And you just kind of have to look at the rule and then also tell me, which rule. So on a worksheet, I may say, is this compound soluble or insoluble? Why? So make sure you also reference the rule or rules that can prove your point. Okay, so practicing determining if something is soluble or insoluble. So pause the video, try these ones. We have calcium phosphate, cadmium nitrate, ammonium sulfide, ammonium nitrate, and cadmium sulfide. So give those a try, pause the video. Okay, so hopefully you figured those out. And I'm going to tell you right now, I don't like the way I formatted this. So I am saying, is calcium phosphate soluble? It is not. So no, it's insoluble. Referencing rule number 5, if you got to that. Cadmium nitrate, soluble or insoluble? Yes, it is soluble. Referencing rule number 2. You can always go back and check that out and verify and understand why this is the correct answer. Ammonium sulfide. Yes, it is soluble. There are two rules that verify that. Rule number 1 and rule number 6. And then we have ammonium nitrate. Yes, it is soluble. That's going to be referencing rule number 1 and rule number 2. And then lastly, cadmium sulfide. No, it is not soluble. It's insoluble, referencing rule number 6. So just make sure you understand those rules. You know how to tell if something is insoluble or soluble, and it can never contradict. So you can't have one rule saying it's soluble and then another rule saying it's insoluble. If you're using multiple rules, it's all the same answer. If not, you're understanding or misinterpreting. Okay, so this is the first video for 14.1. The next part of this, part B, is net ionic equations. And although the actual concept is not long, the equations the examples take me a little bit longer to explain. So I'm actually going to make a separate video for 14.1, but part B, which is net ionic equations.